So we were looking at compression members, wherein we looked at the basics of compression members, as in, what type of stresses they experience, what factors affect the strength of a compression member, and then we also looked at common examples of compression members, then cross sections that are typically used. Then we looked at various modes of failure, and we also looked at the ways to mitigate these failures. Then we looked at an important concept of uh, classification of compression members that's short or long, depending upon the way in that fail, and depending upon, then we further established that it is a function of the slenderness ratio. Then we looked at the behavior of compression members, of short as well as slender compression members. We looked at Euler's formulation for critical buckling load. Then we tried to understand the relation between uh, the buckling stress and the slenderness ratio. And then we, sort of tried to understood the curve that is given in the code. And then we also solved a numerical to back up whatever we had, looked in theory. And, we studied how to classify a section as, if it falls into category A, B, C, or D, if the buckling classification is A, B, C, or D, and then how to use that data and, different tables that are given in the IS code to find out the design compressive stress and hence the design compressive force. Then we also looked at an important concept of effective length. We tried to understand what effective length is, then, the effective length factor for various ideal conditions. Then we try to understand the reason why the values that are recommended by the code are slightly different from the theoretical values, and values in the code are on the higher side, just to make sure that we are reasonably conservative. Now, we're just going to look at some miscellaneous parts. And there's obviously one more numerical that we have to solve. The numerical that we've solved now is, essentially the analysis of a section whose effective length is already given. The only thing that we had to find out is what is the load that it can take. But now today we are also going to look at a design problem, wherein you will be given the unsupported length and the fixed and the support conditions. You would be given the value of the load, and you will have to find out a section that can resist this load. So that is what essentially happens in an actual design. So we know loads, and then we select a section that can take these loads. Before that, just a couple of quick topics for your reference in case you want to select a section for any of your projects. So there are a number of sections that you can choose from to resist the actual load safely, but we have to sort of filter our choices based on some factors. And as an architect, I think the most important factor for you is the type of the structure. So your section should be sort of aligned with the kind of with the overall structure that you're trying to project. So firstly, it depends upon what type of structure are you dealing with. Then the another important very practical constraint is that though there are hundreds of sections that are given in the IS catalog, though there are hundreds of sections given in the manufacturer's catalog, but they don't really manufacture all of them, because not all of the sections are extensively used, and if they cannot really achieve economies of scale, the section would become expensive. Therefore, from that catalog, there are some sections that are easily available. There are some that are not easily available, and there might be some which are not available at all. So before sort of going, jumping from your concept design to schematic design, as an architect, you should know which sections are available in the market and which are not. Which you can easily do by getting in touch with the supplier, and so practically availability of sections sort of limits the spectrum or the range of sections that you can select. And the third important aspect is the ease with which it can be connected to other members. Now, if you're sure that as an architect, you're sure that you don't really want, the connections to be, you don't want visible, bulky bolt connections. You're clear that you want welded connections. Then, you should sort of think about using hollow sections. You can use hollow circular, hollow rectangular, hollow square sections, as you can see in the in the picture below, in the picture behind, that everything is welded here. So the architect has taken taken all the sections are hollow circular sections in various sizes. So it depends upon how easily you want to connect them. But if you're okay with bolted connections, then you really should look for sections like I sections or channel sections, which are easy to connect. They have multiple surfaces which can be used to connect other members, which does not happen with hollow sections, because one face of the hollow sections is not accessible. There's only one face that is accessible. So bolting hollow sections is a difficult task. So it depends upon how easily you want to connect to other members. So this is just a quick table for your reference at a later period of time when you really want to select sections. So if your structural member, you're looking for a structural member for a small span roof whose span is less than 20 meters. So for rafters and bottom ties, you can use double angles. You can use C-section, circular hollow section, square hollow section, rectangular hollow section. And for the members, for the web members, like for the other chord members, you can use single angles and hollow sections. Then if it's a long span roof, instead of two angles for rafters, you can use four angles with a plate, or you can use two channels with a plate, box sections, and so on. And for web members, instead of single angles, you might use two angles, four angles, two channels, and so on. So this is how two channels with a plate look like, and this is how four angles with the plate look like. So you can either make a built-up I section out of it. You can also make a built-up box section out of it by using four angles and plates. Then if you have small towers, then for the leg members or for the columns, you can use circular hollow sections, or you can use two angles. For bracings, again, you can use the same. If you have towers that are about 150 meters high, which is roughly 40 stories. So for the bottom 40-meter legs, so approximately for the bottom 10 stories, you can use four angles, with plates. And for bracing on the horizontal members, you can use double angles. Then if you're looking for something in space frames, then definitely hollow sections are preferred. You might have seen a lot of space trusses, particularly at airports. There are a lot of space trusses. So in that case, hollow sections are really preferred. And then columns of multi-story and industrial buildings, the I sections are most widely used. If it's welding, you can also use box sections. So this is just a table for your ready reference at a later point of time. Any for your design project, or maybe when you're actually practicing as an architect. So as I said before, the numerical that we looked at before was analysis of a particular section. Now we are going to jump into the design of it. Now there's not much variation. We are looking at a very simple case wherein the column is subjected to pure axial compression. So we are not really looking at a beam column whose design is a little involved. But here, it's a simple case of concentric axial force. So what is different in the design procedure? The thing that's different is that we do not know the section, so we have to select a section that is to be used. Now there are a number of thumb rules for selecting sections, but for our understanding and for our level of learning, I've put a very simple thumb rule. The only thing that you have to sort of assume is that you target your slenderness ratio. That this is the slenderness ratio I want to target. For example, if you are planning on using a single I section, your slenderness ratio should fall in the range of 80 to 150. Now, though I have given it for all the members, but from exam point of view, I want you to remember single I section and single angle sections, because that are the most commonly used sections. And if you have a hang of designing these sections, then I think that is adequate. Just give me a moment, please. Yeah. So as I was saying, you can refer this table anytime at any later point of time when you're actually designing. But for remembering, just keep in mind the single eye section and single angle sections. So it's 80 to 150 for single eye and 100 to 150 for single angle. So we'll see how do we when we make this assumption, how do we go forward with this, and how do we use this number? We're going to look at it. But before that, I just want to finish, or I just want to finish discussing column basis. And once we are done with the theory, we'll jump into the numerical. So I believe you must have seen many columns, particularly at train stations. I'm sure most of you have been to train stations, or almost all of you have been to train stations. So you always see that these columns are resting on a sort of a concrete, a bulky concrete uh, platform or pedestal. But before resting that column on that concrete platform or concrete pedestal, there's always a plate in between, and these plates or these arrangement are called as column bases. So basically, these sort of form a medium between the column and the footing. Now, before jumping into this, I want you to ask if you have ever seen a footing that is in steel. Okay, the meeting is still on. You can hear me, I suppose. So, not a difficult question to answer. Have you ever seen a steel footing? Now, I'm sure you have seen steel beams, steel columns, then deck slabs. But what about footings? Can we have footings in steel?
We've seen examples in class, but I haven't seen one personally, like in real life, that we have not seen how a steel footing. And but we've seen some examples in class, like showing us how a steel footing works with like the stacks of them kind of making a crisscross pattern.
Okay, I understand. There are some rare cases in which steel footings are used, and we are going to look at the cases. But in general, uh, we don't see steel footings. Can any guesses as to what can be the reason?
Is it because water? So we will have to treat it a lot.
And why is that?
Um, Steel, it corrodes because of so its structural strength would reduce.
Exactly. So the most important concern here is that ground is going to have soil. Soil is going to have water, salts, minerals. So it is a perfect recipe for corroding steel. So if you place steel in the footing without really covering it, or without really treating it extensively, there's quite a good chance that your section might corrode, and you cannot see. One thing is for sure that come what may, you cannot compromise with the design of footings, because the entire structure is relying on the footing to be adequate, and only then your columns and beams are going to be able to perform their functions properly. So irrespective of how well or how how optimized you have the design of beams and columns, footings are really the base of all of it, and we cannot compromise with the design of footings. So, and that is the reason why steel footings are really not very common. uh, Concrete inherently has resistance to corrosion. I mean, concrete does not corrode. The reinforcement in reinforced concrete does, and concrete protects it. Concrete provides a cover by the virtue of which reinforcement is protected. So, the rare examples that Shravan spoke about are the examples when we use what is called as a grillage foundation. We are going to look at it, and even while using a grillage foundation, we cover everything with concrete. So it's not really a steel footing. It's though the structural mechanism in steel, but still we need a lot of concrete to make sure that steel does not corrode. So now let us look at what are column bases, what are different types of column bases, and what is their function, basically why they are used. So can someone tell me what you know? Can we not place a column directly on a concrete pedestal or directly on a concrete footing? Say we have a box section or an I section. Why can't we place it directly on a concrete platform?
Directly, as in,
Sorry.
directly, as in, like, I didn't understand. the definition directly here? Like just putting it on it and like casting the floor, or why we need a gusset plate in it?
So why do we need a column base? Why do we need this base plate? Why can't we place this footing direct? Why can't we place this column directly on the concrete footing?
We need something to holster it or like bolt it to the ground because steel requires a lot of complex joinery in terms of the bolting or welding.
Okay.
So there
So
needs to be
if
like something to receive that bolting and welding.
receive that bolting and welding. What do you mean by receiving that bolting and welding?
It's like
So
how I'm giving a very oh sorry.
so let us say that I provide a tie beam. So I provide a tie beam right at the junction of the column and the footing to make sure that the column does not now the column does not have a scope to move. I provide tie beams in all the directions. So now fixing the column is not a concern. So in that case, can I place the column directly on a footing?
Okay, my brain is still processing like how that works. Give me 2 minutes, please.
Others are
I'm
also
like
free to.
thinking of the options.
Others, you know that you're allowed to talk in the lecture, right? Come on, it's not a very difficult question to answer. क्या होगा if you just put an I section on concrete and then what will happen? It's a simple question.
Maybe it's for the load to get transferred in a more dispersed way, because obviously steel will be carrying more load than what RCC can hold. So be larger the RCC one.
Okay. So your answer is partially correct that yes, there has to be something to disperse that load. Because but the reason is, the reasoning can be better. Irrespective of what material you use for columns, you use steel or you use concrete, it does not really matter. What matters is that you really disperse the load. So if had you used a concrete column, perhaps it would carry more or less the same load or slightly larger load for the same structure. But the question is not the load here. Just imagine putting an I section on a concrete platform directly and loading it. There's a very high possibility that that section will sort of punch into the concrete footing. Can you imagine that you're just placing a section on directly on concrete platform, and when you load it, there's a high possibility that it might punch into the section. So irrespective of what is the magnitude of the load that it is carrying, a column section is carrying a large amount of load in a very small cross section area. Now, just to help you visualize this, so let us say we are using an I section. Now, all the load that this column is carrying is only in this red area. That's it. Had you used the concrete column, perhaps you would get a column something like this, and your load would be carried by this area. So the stress in an I section is much higher than the stress had it been a concrete section. What is happening is now you are putting this I section on a concrete footing, and the force is basically transferred from the column to the footing by bearing. It is just sitting on it. Okay, it's pure bearing. I hope you understand what bearing is, right?
Not exactly.
So you are bearing on the chair. Your laptop is bearing on the table. So the load transfer is by just sitting on it. The column is simply sitting on the concrete platform or the concrete footing, and the load is transferred just by bearing. So what happens here is that concrete has a certain bearing capacity. Now you already know what FCK is. It is the characteristic compressive strength. It is the in loose words, it is the compressive stress at which the concrete fails. So if FCK is the characteristic compressive strength of concrete, the bearing strength is roughly it is 0.45 times of FCK. The maximum stress that concrete can take in bearing. Okay, this is the maximum stress that concrete can take in compression, and this is the maximum stress that concrete can take in bearing. Now let us try to put some numbers here so that we sort of get a feel of what's happening. So if say this is mild steel, so the value of Fy is 250 megapascals. Let us say 250 megapascals. Now let us say that you are using 30 MPa concrete, or M30 concrete for the footing. So the bearing strength is 0.45 times 30. So this is 13.5 megapascal. Okay. Now, if this particular column is say stressed fully, you have really optimized it so that the demand to capacity ratio is 1. So the stress that this column is carrying is say around 200 250 megapascals. But the stress that concrete can take is only 13.5 megapascal. What will you do to work out a solution for this? Will you increase the grade of concrete so that 0.45 times of 300 is 250 megapascals? And that would be foolish to do, because you do have a structural solution to this. So the objective is not to reduce the load, the objective is to reduce the stress. How can you reduce the stress? If you cannot change the load, you can reduce the stress by increasing the area over which the stress occurs. So what you do is, instead of directly putting a column on the concrete footing, what you do is you provide a base plate here. Now what does this base plate do? This base plate takes all the load from the footing and it distributes over a larger area. So even though the stress in the column is 250 megapascals, the stress in the plate would be lesser, so that the force can be easily transferred to the concrete footing by bearing. That is precisely the function of a base plate. So base plates are used for transmitting loads from columns to its foundation. Base plates principally help in reducing the intensity or the stress of loading and distribute it over the foundation. So this is say this is a column section, this is a concrete footing, and this is a base plate. So the column sits on the base plate and the base plate sits on the footing, which sits on the soil. So as I said before, the safety of the footing, the safety of the column and the overall safety of the structure really relies on the safety of the footing. Now, base plate is nothing but a medium for transferring the forces from column to footing, and therefore it is equally designed to, it is equally important to design the base plate with utmost caution. Um, when we are doing normal beam design, what kind of loading do we have? Say this is a simple support. So there's a UDL, and then there are supports at both ends. So this is a normal simply supported beam. Now what happens in the footing is exactly ulta. So what you have is, so this is your footing, this is a point load, and now there's soil below, and this soil is going to support the footing. So your loading condition is ulta as compared to a beam. Now in a beam, depending upon the analysis, you can say that the load is a uniformly distributed load, or say you might also say that if from the analysis we can really find out if the load is a uniformly varying load, or it is if the load is parabolic. It depends on the analysis, and it's possible that we find out what is the kind of loading that we have in a beam. But in a footing, can we do it? We can approximate it, because see, we can know this value for sure. We can analyze, we can find out how much is the force that the beam is going to carry. But can we find out this? Can we really find out this? We can get a good estimate, but can we exactly find it out? We don't know because it depends upon a number of factors. It depends upon, what is the, basically it depends upon all the nature of the soil itself. What is the bearing capacity of the soil? What is the nature of soil? Is it granular? Is it cohesive soil? It is cohesionless soil, and so on. So you're not going to get into that. But long story short, even though this is a point load, what may happen is, uh, just a moment. So even if this is a point load, what may happen is the soil might exert a resisting pressure, which is something like this, wherein maximum pressure is exerted concentrically below the column, and then there's less pressure on the other side. Or in a different type of soil, you might even experience pressure that is something like this. So the maximum pressure occurs along the periphery of the footing, and the minimum pressure is concentrically below the column. Now we are not going to get into which type of soil behaves in which way. This is really not the point of discussion. But the point is that irrespective of what the load is, depending upon the nature of soil below, you can have different, stress profiles of the soil. So in order to simplify this, what we do is we just assume that irrespective of what the soil is, we just assume that there's a uniform resistance or there's a uniformly distributed soil reaction below the point support. So, if you're expecting something like this, so what you'll do is you'll just average out this and say that the soil provide equal amount of resistance along its entire extent. If it is something like this, you will average it out to something like this and say that the soil provides a uniform amount of resistance or uniform stress below the footing. So that is a fundamental assumption uh, based on which all the footings are designed, whether it be in steel structures or in concrete structures. The assumption remains same that the stress variation is going to be uniform. Now the same applies to a base plate. So if you have a column, you have a base plate, and then you have concrete below this. Even here, we might not get an exactly uniform profile of stress that of the resistance offered by concrete, but we assume that the base plate will experience a uniform resisting force from the concrete footing. So this is the design of base plate is based on this assumption that uniform stress distribution under the base plate. So this is a base plate, this is a column, and this is a pressure distribution below the base plate. Because of concrete, we just assume it to be uniform. Now the question is, what should be the area of this plate, or what should be the planned area of this plate? And I think it's a fairly easy question to answer. So we already know that the bearing stress of concrete, which is denoted by FBR, is 0.45 FCK. Just give me a moment. I just want to verify if it is 0.45 FCK or 0.45 square root of FCK. Just give me a moment. Yes, it is 0.45 FCK. So the bearing resistance of concrete is 0.45 FCK, which means that this is the maximum stress that the concrete can take in bearing. So let us say this is our column, which is an I section. Then this is our base plate. And then this is our concrete footing. Now we want to find out what is the area of this base plate. So we have this data. This is the maximum stress that it can take. Then we also know what is the load that the I section is carrying. Okay. So we already know that stress is equal to force upon area. We have to find out what is the area. So area is equal to the load carried by the column to the maximum stress that the concrete can take. So let us say that we have a load of 1000 kilonewton and we are using M30 concrete as before. So what will we have here? Area is equal to load, which is 1000. Now, since stress is in megapascals, which is Newton per mm square, we have to use the force in Newton. So 1000 kilonewton is 1000 into 1000 Newton, and force is 0.45 times of 30. So 0.45 times 30 megapascals, which is Newton per mm square. So if I quickly solve this, what I get is 74074 mm square. Here Newton gets cancelled, so you just make sure that you are doing it in the right units. So this is the area of the plate that you have to provide in plan. What does this mean? So if you're planning to provide a square plate, so the dimensions of the plate is square root of area, which is approximately 272. So you will provide a plate that is 300 mm. So if you're providing a square plate, this is 300. So this dimension is 300 and this dimension is 300. So normally if it's an I section, we provide rectangular plate, but just for the ease of understanding. That's how we find out how much should be the area and what should be the dimensions of the base plate. It's that easy. But there's another question key. Area is fine, but how much should be the thickness? That's a entirely different design discussion, and we're not gonna get into the actual design of the base plate or how to find out the thickness of a base plate. But I think even for your your design projects, if you even know how to find out the area of the base plate such that it visually looks correct, and technically also it is correct. So this is a very simple procedure of finding out finding out the area of the base plate. So any questions here?
Sorry to go back a bit in terms of the column and foundation connection part, but I just had one question.
Yeah.
When we are actually connecting a column to the concrete base using the specific joineries that we have, are we also sort of reinforcing it as a single member instead of like two members connected to each other? Because if you look at a concrete column on a concrete base, it's a homogeneous material, not a homogeneous material, but acts like a unit, right? Almost
Yes.
monolithically. But since steel does not have that privilege of connecting with concrete like that, this sort of
Yeah.
tries to make it, if not a full singular member, at least closer to that.
Yeah.
That's what I just want to confirm. Thank you.
Yeah. Any more questions? Okay, let me ask you a question. Are you understanding what we have been discussing?
Yeah. Can you go slow? It becomes difficult to write notes at times.
Okay, so whenever you think that you want to write something, just let me know so that I'll pause for a moment. And if there's something that is to be repeated, I'll repeat it. So whenever you want to write notes, just let me know. Shubhangi, are you understanding what we are discussing?
Yes.
Are there any questions?
No. I don't have
Have
any
you,
questions as of now, but
have you understood the function of a base plate?
yeah.
Okay. Sahil, any questions? Sahil, can you hear me? Nanika?
Yeah, I've understood. I don't have a question, but I was just going back to C1. So I just wanted to ask, when you said that if we place directly the column without a base plate, it might just punch into it. Can you just
Yes.
put it out and show? I'm not able to visualize that part.
Okay.
If it's possible.
So I'll try to find an image, but it's
Also,
going to be difficult because normally we don't do it that way.
yeah.
But nonetheless, I'll try to find an image, and when I do, I'll post it in the group.
All right. Thank you.
Okay. Yeah. So this might be a very loose example, but you try standing in water. Are you gonna be able to do it? No, you're just gonna fall inside. But then you place a rubber cork on it. See, a cork platform, or those pads that we have that are made up of cork, and then you try standing on water. Are you gonna be able to do it? Yes. What has changed? So has the load changed? No. So what has changed? The only thing that has changed is the medium between you and water. So what if you had no medium? What would happen is that you punch in water. That you just go into, you just dive into the water. But if you have a cork platform, then what happens is the cork platform takes your load and then it distributes over a larger area, and you don't go inside. So this might not be the best example, but I'm just trying to help you to visualize what might happen if you have a medium, that sort of takes the load and distributes it over a greater area. Let us see if I can come up with a better example. Mm, okay, so just imagine a heap of loose sand or loose river sand laying around. It's very common sight in the it's a very common sight in and around construction sites, and you just try to let us use a stick and let us use uh, the sand. So when you place the stick on the sand, you might notice that the stick sort of goes inside the sand. So imagine that stick as a column, and then that sand as a footing. So then what you do is you just place a plate over the sand, and then you place your stick on that. In that case, your stick will not go into the sand easily, because now you have a medium that sort of takes the load from the stick and it distributes over a larger area. So though the load remains the same, you have principally reduced the stress, because of which the stick does not punch into the sand. So there's a similar mechanism here, but a more involved one. It's not that simple, but principally that is what is happening. Now, if I sort of get a picture wherein there is a column directly sitting on the concrete pedestal, I'll post it in the group.
Thank you.
Yeah, Shreya, are you understanding what is going on? Shreya, can you hear me?
Yeah.
Do you have any questions?
No.
Okay, perfect. Uh, Now, so far we've tried to understood what is the function of a base plate, and how to size a base plate and plan, or how to find out the plan dimensions of base plate. Now, depending upon the magnitude and the nature of the force in the column, and of course the nature of the soil itself, there are number of ways in which we can detail this. We can design and detail this column base. Okay, I just repeat it. Depending upon what is the magnitude and the nature of loads in the column, and depending upon the nature of soil, there are a number of ways in which we can design and detail this base plate. The easiest one is what is called as a slab base. So what happens in a slab base is you have a very thick base plate. So this column sits on this base plate, You connect the flanges of this column to this base plate by using angle sections. So there's an angle section here, there's an angle section here. And then you connect the base plate to the concrete pedestal using what are called as anchor bolts. Now, this sketch also shows this angle sections that are connecting the web of the column to the base plate. Now, these are optional, but these are provided just to make sure that the column is not dislocated. So, but the main members are these angle sections which connect the flange of the column to the base plate, and these anchor rods or the anchor bolts which connect the base plate to the concrete footing. Now, such a type of simple arrangement.
Bhargav, sorry to interrupt, but are you
Yes.
sharing screen?
Oh, yes, I am not sharing screen, but I wanted to. Thank you for reminding. Okay. So this arrangement is called as a slab base arrangement. Wherein what is happening is, so this is our column, this is our base plate. So we connect the flanges of the column. So this is one flange, this is another flange. So we connect the flange of the column to the base plate by using these angle sections, which are called as cleat angles. And then we connect the base plate to the footing using anchor rods or anchor bolts. Now this is the simplest arrangement, and this arrangement is used only when the magnitude of actual load is less and the actual load is concentric. So if you have a very simple typical structure which is not highly loaded, in which the bending moment is very small, it's majorly actual load, then you can use such a type of arrangement. Okay. So if I have to show it in plan and elevation, so this is plan. So this is our base plate, this is our I section, and these are our angle members. So we bolt the flanges of the column to the I section, to the channels, to the angle section, and then we also bolt uh, the angle section to the base plate. Now these web cleats are optional. The angle sections connecting the web of the column to the base plate are optional, and they are used only when only to make sure that the column stays in its position. So web cleats connect the column web to the base column and to the, yes, this is something we've discussed. Now let's talk about anchor bolts. So have you heard of these bolts before, anchor bolts?
Yes. Not very technically in terms of how they work, but what they do in a journey we studied.
Okay, so let us quickly look at a video and try to understand the use of anchor bolts.
Are you sharing screen?
Just a moment, I will.
Okay, sorry.
this is a slightly different type of base plate, so or the base slab base arrangement. I did not want you to, I wanted to understand how the anchor bolts are placed, or how the anchor bolts. Uh, so in this, the base plate is already welded to the column. This is the base plate. This is the anchor bolt.
Hay na, tak open na.
We have anything more? Again, here you see the base plate is already connected.
Юр, пускай они сначала поставят ее, а потом...
Юрка не видит, закрой.
Нет, нормально.
So from these videos that we saw, what do you think is the function of the anchor bolt? Can you hear me?
The video was a bit I don't want to say blurry, but it was a bit choppy on my end. Like it was skipping frames a bit.
Okay.
Kind of a side thing, but could you maybe upload them to files because I don't know, or if in the recording they'll be fine, then I don't think it'll be an issue. But
Okay.
just in case, could you upload the videos to the files as well?
Okay.
Thank
So
you.
in these videos, we saw that the main function of the anchor bolt was to keep the column, in position during construction. It's a very basic function. Key, when you're placing the column over the footing, it has to be exactly aligned the way it is given in the drawings or the way it has been designed. So anchor bolts make sure that happens, and then they also provide resistance against any shear that might occur in the column. And they are called anchor bolts because they anchor the column against any uplift because of lateral loads. So you can imagine if there's say wind load or earthquake load acting on a column, some portion of the structure or the columns in some portion of the structure might experience tension. Under gravity, they would be under compression, but under lateral loads, they are under tension. Now, if there are no anchor bolts, or if there is nothing that is anchoring the column to the footing, the column might just pull off, or it might just get uplifted. So in order to prevent that, anchor bolts play an important role. So I've just placed this in the presentation, place the function in the presentation. The next type, or the next condition wherein the magnitude of actual load is quite high, and there's also bending moment. So the column is not an actually rotated column, but a column with actual load with a significant amount of bending moment. In such a case, what happens is we use two more plates, which are called as gusset plates. So the one that you see in gray is our column. Now, what you see in blue is an optional cover plate. You can provide it, you cannot provide it. It's an optional, and it depends upon the sort of detailing that you're doing. But the minimal element that we have is that we have a column, and then this is the gusset plate that connects the column to this angle member. So you bolt this gusset plate to the flange of the columns, and you further down the bolting to this angle section, and you do a similar thing on the right side, And then you have these anchor bolts connecting the base plate to the concrete footing. So everything remains the same except that we have these two gusset plates, which provide an additional resistance against bending moment. So I don't want to get into the mechanism, but I just want you to understand and remember that whenever we have bending moment, we use what is called as a gusseted base, wherein there are these two additional gusset plates, which help in transferring the additional tension and compression due to bending moment. So used on axial loads is relatively large along with a substantial bending moment. It consists of two gusseted plates, one attached to each flange, and a base plate. Now, one thing that you would like to note is that in a gusseted base, the thickness of the base plate is relatively smaller because you add these gusset plates and you sort of alter the mechanism by which the transfer occurs. So in general, it is found that the thickness of the base plate in gusseted base is slightly smaller, or it is slightly thinner than what is used in the slab base. So if you just want to look at a structural detail, so this is an I section flange web. These are the web cleats, just to make sure that the column does not dislocate. Then this is our gusset plate. This is our angle section. And these are our anchor bolts, base plate, and concrete base. And the final type is the one that is used when the soil is really weak, as in really, really weak. In that case, simply providing a base plate is not going to help us, transfer, transfer the loads in the footing and then into the soil. In that case, what we use is, in that case, we use what is called as Grillage Foundation. So, Grillage Foundation principally consists of these sets of beams which are placed, over each other in the perpendicular direction. So, what we do is we place firstly we sort of level the soil. Then there's this concrete pad, 150 centimeter, 150 millimeters concrete pad, and then we place the first set of beams, and these beams are separated approximately 100 to 300 mm, and then we place the second, and if required the third. Then there's this base plate, and then there's a column, and this entire arrangement is then poured, the concrete is poured in and around this entire arrangement just to protect it from any possible corrosion. Now, just to give you a sense of scale for this, or how large this the arrangement could be. So this is our leveled concrete surface. This is our first set of beams, which are placed approximately at some distance using these elements, which are called as pipe separators. Then you have another set of beams which are perpendicular, and again they are separated by some distance using these pipe separators. And then there's I think this is a different type of platform, but you can also, I think there's an additional layer of concrete. It's not clear in this, but here it is directly placed on a plate. Here maybe they have provided an additional platform, and then a base plate, and then a column sits on that. So this type of an arrangement is called as a grillage foundation. And in this entire arrangement would again then be, poured concrete would poured in and around all these beams. So this is a very short introduction to what grillage foundation is. And with this, I think this is all you need to know about compression members, about base plates, and about the general behavior of compression members and how to analyze. And now we are going to look at how to design compression member. So any questions?
So if a grillage foundation is encased in concrete,
Yes.
why are we worried about the water permeability since already it's acting like a concrete member in terms of water management, right? Because the water is encased in concrete and we can always protect it from water that way.
Yeah.
So in a sense, even RCC bases are in some sense just steel encased in concrete, right? The reinforcement is as prone to water damage and erosion than the corrosion than as the steel base,
That is
the
correct.
grillage foundation.
That is correct. But in a reinforced concrete footing, concrete has a structural function. concrete resists shear, concrete resists flexure, and you design a footing just like an inverted beam. So, in footing, concrete has a structural in reinforced concrete footing, concrete has a structural role to play. Here, the entire point of providing concrete is to protect steel from water, from soil, in short, from corrosion. It does not have a structural role to play. Do you understand the difference? Can you hear me?
I think my audio cut out for 10 seconds or 5 seconds just now.
Okay, so could you listen to what I said?
I think you said something about a difference and then your voice cut out.
Okay. So, in reinforced concrete footing, concrete has a structural function. Just like a beam, in a reinforced concrete beam, concrete and reinforcing steel act together to, create a resisting moment. Similarly, and also they act together to sort of resist shear. Similarly, in a footing, concrete and steel act together to resist bending moment and shear. So, here concrete has a structural function. In Grillage Foundation, it does not have a structural function. It is used only to cover steel. It is only to make sure that steel does not come in contact with water or soil, so that it does not corrode. Is it clear now?
Yes, thank you.
Okay. Uh, any more questions? Okay. So we'll just take a small break because I think this there's been a lot of information that has been shared for the last hour. So I just want you to sit back and relax for a couple of minutes, and then we'll solve a simple design problem, and then we'll wrap up compression members. So we'll take a small break of 3-4 minutes. If you have any questions, I'm here. Else we can resume with the numerical.
Could you please upload the compression members PPT to the file?
Yes,
Because I
today I
think
will.
it's easier to refer it when we have the file, just to go
Yes.
through it in a quick meeting.
Yes.
Hello, Bhargav, are you talking? Because we can't hear anything.
So I've been talking for the last 4 minutes without unmuting myself. Okay, so we will resume. Please write down. Design a column. Design a column to support a factored axial load. To support a factored axial load of 1600 kilonewton. To support a factored axial load of 1600 kilonewton. The column has an effective length of 5 meters. The column has an effective length of 5 meters with respect to z-axis. With respect to z-axis and 3.5 meters with respect to y-axis. And 3.5 meters with respect to y-axis. Assume Fy is equal to 250 megapascal. Assume Fy is equal to 250 megapascal. I'll repeat the question. Design a column to support a factored axial load of 1600 kilonewton. The column has an effective length of 5 meters with respect to z-axis and 3.5 meters with respect to y-axis. Fy is equal to 250 megapascals. So let us try to understand the given data. First is that there's a factored axial load of 1600 kilonewton. Now, I hope you understand the difference between factored axial load and service axial load. So if the question would say the service axial load, which would mean it is P, which is equal to 1600. Let us say it is 600 kilonewton. The first step would be to find the factored axial load or the ultimate axial load or the design axial load. So the factored axial load, which is denoted by say PU, this is equal to 1.5 times P. So this would be 1.5 times 1600, which will be 2400 kilonewton. So you would design your column for 2400 kilonewton had this been a service axial load. If the factored axial load, it's already multiplied by 1.5. So this is your design load. Then
So
the
since
next,
we have a factored, sorry, since we just confirming, since we have partial, so here we don't have to worry about the partial safety factor because it's already been factored in, right?
yes,
We don't have to
1.5.
worry about the design.
Yes,
Should come to
1.5
act.
is yes, 1.5 is the partial safety factor for load. Which, if you do not remember, please go back to presentation number 2 and go to the partial safety factor for loads. Understand why we use partial safety factor for loads and what are the common factors for dead and live load. So the given data is that the factored axial load is 1600 kilonewton. Then what has been given is the effective length of 5 meters. So you already have an effective length. You don't have a unsupported length. So the effective length, which is denoted by KL, oh, keyboard is going crazy. So effective length about z-axis is 5 meters, and the effective length is this. Effective length about y-axis is 3.5 meters. Okay, just give me a moment. Okay, so now the question is, what the hell is this? Why do we have two effective lengths? Can someone answer this question?
Is it because the load is not directly acting in a vertical fashion, but there's also an angular component?
That has got to do nothing with effective length. Effective length is a function of end constraints only and only.
Then is it because the end constraint? So then let me rephrase that. Is it because at the end constraints are different from the way the column is, like the base is wider than the actual column?
Okay, so I'll answer this question. Let's see if you understand it. So let us say this is our column section. So when we are talking about bending about the major axis, okay, so we are concerned about the connection or the framing about the major axis. So we are concerned about the framing here, or the amount of fixity that it has in this direction. Okay, so the nature of this framing governs what is the effective length when we are bending about. So this is our major axis, Z axis. So the fixity that it has in this direction governs what is the effective length in Z direction. Now, when we are talking about bending about Y direction, so this is our Y direction, and we are talking about bending about Y axis. In that case, the framing in this direction, or what is the kind of beam that is coming and framing here, or what is the kind of connection that the column has in this direction, governs what is going to be the effective length in Y direction. So basically, we can have two different effective lengths for the same column about different axes. So if I go back to the presentation, that is why we say that effective length of a column in a given plane. So it may be, if bending about Z axis, or it may be bending about Y axis. So if I have to, explain it in more simple terms, let us just take example of reinforced concrete. If we want to, so let us say that we have a column, and there are two beams that are framing in this column. So this is, beam in one direction, this is beam in other direction. You just give me a moment to think. This is a correct example. Okay, let me make a slight modification here. Okay, so if I take an elevation here, this is our column. Let us say this is our slab, and this is our beam. And if I take, so from this you understand that, say, roughly this beam is 600 wide and say 1000 deep, and this beam is say 200 wide and it is 500 deep, or not even 500. Let us say this is 300 deep. Okay, So this beam, which has a very high value of I, it provides a larger fixity, or it provides a larger uh, bending strength, or what can I say? It provides a larger fixity to the column as compared to this beam that has dimensions of 200 and 300 and a relative less value of I. So when we are talking about bending this column in this direction, it has a larger fixity. When we are talking about bending of the column in this direction, it has smaller stiffness. And therefore, there might be a case. Now, see, we are not going to get into how to calculate this and what are the values when we have such conditions. We're not going to get into that. The only point of giving a example in which we have two different values is to make you understand that we might have two different values of effective length in two different directions based on what is the framing in that particular direction. So the effective length about z-axis is 5 meters, about y-axis is 3.5 meters. And the next data that we have is Fy is equal to 250 megapascals. Now we want to find out a column section that will resist this data, that will resist this actual load. So how do we start? Now, if I go back to the presentation, so we are going to use the most commonly used section, that is I section. So for a single I section, the slenderness ratio is in the range of 80 to 150. Okay, so let us start with an assumption. So assume the slenderness ratio to be 100. Okay, in the range of 80 to 150. 100 seems an okay number. You can use 100, you can use 10, 20, anything, 110, 120, anything you want between 80 and 150. 100 seems a reasonable number. So let us start with assuming a slenderness ratio of 100. Okay, I already know my slenderness ratio value. So if I have to compute the radius of gyration, so slenderness ratio is scale upon r. My keyboard is on freeze, I have to do something about it. So slenderness ratio is KL upon R. Now we know this, we can find out this. So let us say RZ, radius of gyration about Z axis. Again, this is subscript. So RZ is equal to KLZ upon 100. So this is equal to, make sure that you are using consistent units. So 5000 mm divided by 100, which is 50. What is the unit of R? Can you hear me?
Kilowatts.
Kilowatt.
Meters. Oh no, wait. Slenderness ratio is height by area. Square meters?
Okay. Listen to what R means. R is radius of gyration. Does that ring a bell?
Meters.
Okay, R can have a unit of. So basically, R is a distance. So distance will have units of meters, centimeters, kilometers, and so on. Okay. So here, see KL, lambda is the slenderness ratio. Slenderness ratio is just a ratio, it does not have any unit. So R is going to have the same unit as KL. So if you use KL in meters, you will get R in meters. If you get K in centimeters, in and so on. Here we are using in millimeters, and therefore the unit that we have is millimeters. So this is the radius of gyration about z-axis. Now, what is the radius of gyration about y-axis?
Sorry, but Bhargav, how does this
Yeah.
length ratio have no unit? Because technically it's like length by area, right? So it
It is
should have
length by
some.
length.
Length by actual length, right? It doesn't take the area into consideration. Just for. Right. Thank you.
Yeah. So this is KLY upon 100 again. So KLY is 3500. 3500 upon 100 is 35 mm. So now we have two radii of gyration. So we just have to select a section such that its Ry value is greater than 35 and Rz value is greater than 50. So we started by assuming a slenderness ratio, which we know should be in the range of 80 to 150. We started with the number 100. Then we found out what are the radius of gyration, what are the radii of gyration that are required. So we found out Rz because we already knew KLZ. So KLZ upon 100 is 50. Then Ry is KLY upon 100, which is 35. So we have to select a section such that its value of Ry should be greater than 35 and its value of Rz should be greater than 50. Okay, so we'll quickly go to our steel table. So this is a steel table. We'll go to I section. And again, we'll use a very commonly used type of I section, which is MB. So we'll look for an ICE MB that has a value of. So here we have Rx and Ry. Don't get, again, as I said, don't get confused. Here, this axis is noted by X, but in I score it is denoted by Z. So X means Z and Y means Y. So don't get confused there. Try to understand what it means. So now we have here these values are given in centimeters. So what we'll do is, just for making sure that we don't mess up with the units. So this is 5 centimeter. And this is equal to 3.5 centimeter. Okay. So I'll just open them side by side. So we are looking for a section that has an Rz value of greater than 5, Ry value of greater than 3. So let us look at these values. 4, 5 point. So we can, so in terms of Rz, we can use this section since this value is greater than 5. But this is not. Therefore, we cannot use this section. Now, if we see in this group, there's no section that has a value of Ry greater than 3.5. So let us go to next page. So here, this one, 3.52. Which section is this? ISMB 500. So ISMB 500 has a value of Ry that is greater than 3.5 and a value of Rz that is greater than 5. Okay. So just for your reference, I'll write it here. Referring steel table, select a section that has RZ greater than 5 centimeters and RY greater than 3.5 centimeters. So as we saw, select ISMB 500. So like we did last time, we are going to need some data from the steel table. We'll start with the area. So the area is 111 centimeters square, which is 11100 mm square. Then the depth is 500 millimeters. Width of the flange is 180. RZ is 20.2 centimeters, which is 202 mm. RY is 35.2, which is with 3.52 centimeters, which is 35.2 mm. Now, since it turned out to be the same section that we used in the analysis, the step number 1 remains the same. So the buckling class of cross section is H upon BF, 500 by 180, which is greater than 1.2. Thickness of flange is 17.2, which is less than 40. Therefore, if we go back to IS code, if this condition is met, then for buckling about Z axis, the buckling class is A. For buckling about Y axis, the buckling class is B. Now, step number 2, effective length. The effective length is already given, so we can skip this step. Okay. Then the next step is to find out the slenderness ratio. So for the slenderness ratio about Z axis, what we have is so KLZ is slenderness ratio is KL upon R. So KLZ is 5 meters and RZ, which we'll get from here, RZ is 202. So 5000 upon 202 is 24.75, and slenderness ratio about Y axis, which is KL upon RY. So KLY is 3500 and RY is 35.2. So 3500 upon 35.2 is approximately 99.43. We can approximate it to 99.43. Okay. So now the question is, we have two values of slenderness ratios. In order to find out FCD, which slenderness ratio should we consider? Or do you want to consider both slenderness ratios, find out two values of FCD, and then use the lower value to find out the design action load? I know I'm already overshooting the time a little bit, but since when the flow will just take a few minutes to finish this, so that we can give the design of steel beams a fresh start that it deserves from the next week. Do you understand my question? Okay, I take it a no. Can you hear me? Can you guys not hear me?
We can hear you.
Okay, so did you understand my question? Okay, I take it a no. So when we analyzed the section, we found out, we found out the effective length, and we found out two slenderness ratios. So the slenderness ratio about z-axis and slenderness ratio about y-axis. What we did is then we know that for buckling about z-axis, the buckling class is A, and using this we refer to this table, and then we found out the value of FCD about z-axis. Then we looked at the slenderness ratio about y-axis. We knew the buckling class. For this, we went back to the table, did an interpolation, and found out a value of FCDY. Now we had two values. We took the minimum value, we multiplied it by area of the cross section, and that gave us the value of design actual load. But towards the end of the lecture, I told you that we need not do this in the examination because, or in general, we need not do it because any slenderness ratio, okay, now a very basic discussion again, greater the value of slenderness ratio, smaller is the value of actual load. As the slenderness ratio increases, the actual load decreases. For the same column, we have two slenderness ratios. So the slenderness ratio that has a greater value is going to give us a lesser value of actual load, and that is going to be our design actual load. So my question here is that now we have two slenderness ratios. One is 24.75, another one is 99.43. So which of these ratios would govern the design, meaning which of these ratios would give us a lesser value of actual load?
Second one.
Thank you for answering that. Second one, right? The greater the slenderness ratio, the lesser is the amount of load that it can take. Okay, so this slenderness ratio would govern, meaning that this slenderness ratio would give a smaller value of actual load. And therefore, we would not proceed with this slenderness ratio. Because if we have provided a column that satisfies this, we are naturally covering this as well. Okay, so we are not going to proceed with one, we are going to proceed with two. So for buckling about y-axis, the buckling class is B, and the value of KL upon R, that is the slenderness ratio for Y, is 99.43. Okay, so now we know the value of slenderness ratio, we know the buckling class. Now we just go back to our ICE code. So ICE code gives tables for different buckling classes. So this is table 9A for buckling class A. We don't require this because our buckling class is B. So this is design compressive stress for buckling class B. Here, our yield stress is 250 megapascals. Therefore, we have to look at this column. And the slenderness ratio is 99. So we have to look for a number between 90 and 100. So I'll just quickly take a screenshot. Okay, so we have to look at 90 and 250, which is this number, and 100 and 250, which is this number. Okay, so what do we have? For KL upon R FCD. So for a KL upon R value of 90, then R value is 99.43, is it? Yeah, 99.43, and then 100. So for 90, the value is 134. For 100, the value is 118. Can someone approximately tell me what is going to be the value for 99.43 without doing any calculation? I'm sort of getting a feeling that you've not, like, none of you have revised anything from the last lecture. This is simple interpolation. We know a value for 90, that is 134. We know a value of 100, which is 118. We are trying to find out a value of 99.43. Without calculating, can you guess what?
117?
Yeah, it would be, you can use a value of
117.5.
118 directly. Because see, 99.43 is almost 100. We are looking for a value between 134 and 118. So you'll get a value like 117, 118. So,
Right.
if you are in a hurry in the examination and you sort of almost certainly know that the value, is going to be close to this, I'm okay if you assume it without doing the actual calculations. Now, I want you to do this actual calculation on your own. But since you're short of time, what I'm going to do is I'm going to say FCD is approximately equal to 117. What is the unit?
Megapascal.
Megapascal, because it is stress. Okay, and then the last step is to find out what is the load that it can take. So this is equal to AE into FCD. What is the effective area? 11100. So 11100 times 117. So this is equal to 1299 kilonewton, which is approximately equal to, okay, something went wrong here. Okay, something has gone wrong in this calculation. Give me some time to figure it out. We will quickly revise this, again in the next lecture, and then we'll start with the design of steel beams. So I